This is a screencast on Unit 2 for AP Chemistry on bonding, and I'm going to cover something under Topic 2A, deviations from ideal behavior for the most part with the gas laws. So deviations from ideal gas behavior. At high pressures and low temperatures, gas particles come close enough to one another to make the two postulates of the kinetic molecular theory invalid. The assumption that gases are composed of tiny particles whose size is negligible compared to the average distance between them begins to fail. When the gas is pressurized into a small space, the gas particle's size becomes more significant compared to the total volume. The assumption that the forces of attraction or repulsion between these two particles in a gas are very weak or negligible begins to fail. So low temperature means less energy, so the particles are attracted to one another more. Under these conditions, high pressure and low temperature, gases are said to behave non-ideally or like real gases. This has two consequences. When gases are compressed to high pressures, the size of the gas particles is no longer negligible compared to the total space occupied by the gas. Therefore, the observed total volume occupied by the gas under these real conditions is artificially large, since the gas particles are now occupying a significant amount of that total volume. Previously, under ideal conditions, the gas particles' size were negligible compared to the total volume occupied by the gas, and therefore the observed total volume was approximately correct. The real gas situation necessitates the need to correct the volume by subtracting a factor. The actual pressure of a gas is lower than one would expect when assuming there were no attractive forces between the particles, because in a real gas, the particles are attracted to one another. They collide with the walls with less force, and the observed pressure is less than in an ideal gas. This necessitates the need to correct the pressure by adding a factor. So the van der Waals equation, you will not be asked a calculation question from this equation, so don't freak out yet, but you may be expected to relate the relative sizes of A and B to the deviations previously listed. For example, gas particles that have a relatively strong interparticle between particles attraction for one another would have corresponding relatively large values of A. There's A, since their pressure needs to be corrected by a larger factor, and that relatively large gas particles would have a correspondingly relatively large value of B, there's B, since they take up a larger volume. Root mean square. The root mean square, sometimes called the RMS, speed of the velocities of gas particles is the square root, here's the square root, of the averages of the squares of the speeds of all the particles in a sample of a particular temperature. What did I just say? The root mean square speed, or URMS, can be calculated using the root mean square root of 3RT divided by M, where R is a little bit different R. It's the universal gas constant, but it's 8.314 kilograms, M squared S minus 2 moles minus 1, K minus 1. Of course, temperature has to be in kelvins, and M stands for molar mass of the gas in kilograms per inverse moles. So a larger molar mass means a smaller root mean square. So oxygen versus nitrogen. Oxygen has a smaller root mean square because the molar mass is bigger. Oxygen is 16 times 2, which is 32, and nitrogen is 14 times 2, which is 28. So since oxygen has a bigger mass, its speed is smaller. And a larger temperature means a larger root mean square, and vice versa. Effusion, a passage of a gas through a small hole into a vacuum. And if that doesn't make you laugh, I don't know what does. Diffusion is the process by which a homogeneous mixture is formed by the random mixing of two different gases. You have all experienced diffusion. Graham's law. The rate of effusion is inversely proportional to the square root of the mass of its particles. You will not be asked to perform a calculation of this on the AP exam, but you should appreciate that smaller gas particles effuse and diffuse at higher rates than larger gas particles. So the rate of the first gas divided by, it's always this comparison or ratio type thing, over the rate of the second gas equals the square root of the molar mass of the first gas over the molar mass of the molar mass of the second gas over the molar mass of the first gas. So once again, smaller gas particles effuse and diffuse at higher rates than larger gas particles. Duh. Henry's law, temperature and solubility of gases. At higher pressures, more gas particles strike the surface of the solution and enter the solvent, meaning the concentration of the gas dissolved in the solvent is greater. Gas solubility usually decreases with increase in temperature of the solution, since the gas particles have more energy and can escape from the solvent, meaning less gas is dissolved in the solution. So before we talk about this Coke scenario in green, this past summer the temperatures were quite high in Seattle, and they were really concerned, and I think they still are concerned, about the salmon swimming up the rivers. The temperature's been so high that the gas, oxygen in particular, that the fish need has escaped from the water, because at a certain temperature really starts to leave the solution. And if the fish don't have the gas in there, the oxygen gas they need, they're going to die. So there's many concerns for the salmon going up the rivers. Besides temperature, there's also that oxygen concern. So think about a Coke. When it is most fizzy or carbonated, when does it have the most carbon dioxide dissolved in the sugar solution? The answer: when it is cold, when the CO2 does not have sufficient energy to escape. And when it is sealed, it's under pressure. So when the CO2 is forced into the solution, so warm Coke usually equates to flat Coke, as if it's been sitting there for a while. And that's the end of the notes for this section.